today we are starting a journey on logistic regression, and we'll be looking at simple logistic regression and multiple logistic regression. Now, what is the objective of this class is that at the end of this class, you should be able to examine association between categorical variables using contingency table, fit a logistic regression, evaluate a logistic regression, use independent variables to make predictions on the dependent variable, of course, using the logistic model. Then the content, we look at three basic things: contingency tables, logistic regression. Under logistic regression, we're looking at the simple and the multiple. Remember, 2 classes ago, I said simple is when you have one independent variable on a dependent variable, while multiple is when you have 2 or more independent variables on a dependent variable. The dependent variable will always be 1. All right. Now, linear and logistic regression, it's important we are able to differentiate both. Regression is a statistical relationship between 2 or more variables in which a change in independent variables or variable is associated with a change in dependent variable. That's what regression is all about. The logistic regression is used to estimate discrete dependent variables. When we learned about the linear regression model last 2 weeks, we were using dependent variable that is a continuous variable. Dependent variable 1 that is a continuous variable. So that was why we used linear regression model. So we said, or we demonstrated, that it can be simple and it can be multiple. Simple being that you have one independent variable, and multiple you have more than 1 independent variable. All right. So for logistic regression, it is used to estimate discrete dependent variables, usually binary values like 0 and 1, yes and no, present and absent, and so on, from a set of independent variables. It helps to predict the probability of an event by fitting data into a logistic function. All right. So anyway, you see LR now, I'm talking about logistic regression. Logistic regression is one of the most popular forms of the generalized linear model. If you remember, for the last 2 weeks, we've been using LM for linear model. This will be using GLM function, that's generalized linear model. It is capable of using continuous and or categorical predictors, that's independent variables, to predict a binary outcome. All right, so like we said, for the linear regression, we can have the independent variables to contain continuous variable and categorical variables. The same thing applies here for logistic regression. The only difference is that for linear regression, the dependent variable is a continuous variable, while for logistic regression, the dependent variable is a categorical variable. And the scope of this training, we are limiting it to binary dependent variable that has 2 categories or 2 factors, 0 and 1, present and absent, like I've said before. Okay. So while the linear regression model is applicable to continuous dependent variables, LR is a classification problem. All right, that's what I've been saying for a few minutes now. All right, so look at graphically represent both of them. Remember when we were from the beginning of the class that we've been, even before we started visualization, we've been doing scatter plots and we'll be fitting the regression line, also called the trend line. So the first one here, which is B, linear regression, represents what the objective of the linear regression is: to have just like in a linear, to establish a linear relationship between the variables. While for logistic regression, like I said, is a classification problem. The trend line wants to clearly demarcate, the model should be able to clearly tell us whether one factor is being predicted or the other one is being predicted. All right. So the difference between linear regression and logistic regression, which I've been saying all along, here. All right. So you can check them out. Now, if you remember the linear model, this is the logistic regression model. It's quite. This is a much more simple one. We'll see a much detailed one later. But basically, this diagram represents what the logistic regression is about. Well, we have x1, x2, x3. These are the inputs. They are our independent variables. So here we have 3 independent variables, and these are the weights. That's the coefficients attached to them after fitting the model. So now, what the model is trying to do is to predict someone or a group of people, using a group of people to know the pattern at which these independent variables predict whether they are happy or they are sad. So this is the outcome, the dependent variable, happy and sad. Now, I need to say something that most times in across softwares, the first one is being predicted. So, we have two possible outcomes. Either a person is happy or sad. So, what are these independent variables predicting? Are they predicting happy or they are predicting sad? So most times we have the reference points, rather, let me put it that way. The reference point is the first one. For R uses it's use the first one, which is usually arranged alphabetically. Just like here, H comes before S. That means happy comes before sad. So R is going to make this the reference point. It's going to predict this. Of course, when you know the probability of someone being happy, you automatically know the probability of that person being sad. So that's the essence of logistic regression. Unlike the linear model, you have just one continuous outcome. All right, so I just want to go through all the PowerPoints. It's not much. I think we probably have two left here, so that we can go into R and demonstrate, show by demonstration. Now, look at logistic regression, dealt about contingency. Although we won't use this so much today, in the next class we will see more of this in the model evaluation. But however, the contingency table is usually a 2x2 table. It can be more, but it's usually a 2x2 table where the outcome is usually put in the row heading, and the treatment usually put in the column heading. Now, these arrangements are very important. You would want to put, like I said, your reference outcome as the first here. Now you want to put the treatment, your reference treatment also. That's for the your reference treatment also. Really, your independent variable as the first one here as well. This might be abstract, but very soon we'll go into the practicals to see them. All right. Now, for the R code to create tables, I intentionally put this here. Now the treatment should come first. That means your column headers, your column, whatever it will be in your column should come first, and whatever you want to be on the row should come second. So column comes before row in the R code. All right. Now, for odds ratio, there are a lot of things we can calculate from this table. A whole lot of things we can calculate. And what we're concentrating on today is the odds ratio. Of course, we would see chi-square as well, because looking at categorical variables, the outcome and the exposure, the outcome and the treatment variables are categorical variables because they have two levels. All right. So when we're talking about categorical variables, we are basically talking about association between them. And of course, chi-square comes to mind. Fisher's test comes to mind, and there are a few other ones as well. All right. So we'll be looking at chi-square today. I'll also be looking at odds ratio. So while interpreting the logistic regression, we'll be talking about odds ratio a lot. Now, odds ratio greater than 1.0 indicates that the odds of exposure among case group are greater than the odds of exposure among controls. Now, okay, the exposure might be a risk factor for the disease. Now, less than 1.0 indicate that the odds of exposure among case group are lower than the odds of exposure among control. All right. Now, this is among the treatments, we have the case and we have the control. Among the treatments, we have the case and the control. Now, I use students here because in the example we want to do, this will be students and this will be non-students, while this will be defaulters and those who are compliant. So we'll be looking at a data set popularly known as the loan data set. Now, it's looking at, we have three independent variables predicting whether a person will default or will be a compliant customer. Yeah, those who have accessed the loan. And part of the independent variable is whether a person is a student or not. So for this table, the case is students, while the control are non-students. Whether you are working class or unemployed, you are a non-student. All right. So now, saying that an odds ratio of 1.0 indicates that the odds of exposure among case group are greater than the odds. That means the odds of exposure here, the odds of this happening among students is greater when we have odds ratio greater than 1.0. Usually, odds ratio goes from 0 to 1. Yeah, from 0 upwards. Sorry, not from 0, from 0 upward. All right. Okay. Now I use this here because usually, well, my experience most times we use it a lot in medical sciences. All right. Again, OR, odds ratio greater than 1, means that greater odds of association with exposure. Now, odds ratio can also be, apart from giving us the likelihood of something happening or something being present in a group, it also shows association as well. So when odds ratio is greater than 1, it means that greater odds of association with the exposure and outcome. And when odds ratio is 1, it means there is no association. While if it is less than 1, it means there is a lower odds of association with the exposure and outcome. All right. Now, for a simple logistic regression, we have this model, which we are going to see in detail. There. Now, looking at this, we have the this is the regression model for simple linear regression model for simple regression, because we have the model constants, the B naughts, and the or beta naughts, then B1 and the independent variable, just one independent variable. So just fitting them here, that's the difference between logistic and linear regression, would give us the predicted value. All right. Then for multiple logistic regression, we have these models here that we can interact with later. All right. Then for the class evaluation, said carry out the class example again without removing the outliers. So in the example we'll be looking at, there are a few outliers there that we'll see how to remove them. And then you'll be asked to carry this out again. The essence of the class evaluation is that you should be able to go through the class all over again and see where you have challenges. Then we have the assignments. Of course, we have the assignments that will be created, we posted on Google Classroom as well. Then let's not forget, the assignment for last class will also be posted as well very soon after this class. All right. So that's it about the PowerPoint. So I wanted to do away with the PowerPoint and start with R. All right.
Excellent, sir.
Now, if you have,
Excellent, sir.
okay, yeah.
How is
Yes, I can hear you.
How is logistic regression different from 2-bit or logistic regression?
Okay. The logistic is the same as logics. It's simple as logics. While like a 2-bit is okay. When we have, I didn't want to go into that area, but let me show you something. Okay, like I said, that when we have two binary outcomes, we say it's logistic regression. So we can have binary logistic regression, and that's what we are doing here. When we now have 3 outcomes, then we have multiple. We have multiple. But so for logistic regression, is the same thing as logics. While 2-bits can have more than 2 factors in the dependent variable. So in some places you see that they are using logics for logistic regression, but the general name is logistic regression. In fact, there's okay, I'm not sure if it's SPSS.
Regression is also specified.
Is it also specified?
I mean, how do we write the equation? Is it the same way we write for logistic regression, or is it a little bit different from that?
Yeah, it's a little bit different from logistic regression. That's for 2-bits, right?
2-bits, yes.
Yeah, it's a little bit different because, like I said, for binary logistic, we have just 2 outcomes. Let me show you that. Where are you? Okay. Okay. So here, I think we have 2 possible outcomes. So in breaking it down, this will be quite different here. We'll have a quite different model here in breaking it down. All right. Okay. So let's start. Now we have our left. Let's start and hope that we'll finish. We will finish anyway. So the first thing we do is to set our working directory, which we've done over and over again. The code to set that is set WD. Your working directory is that place in your computer or on the cloud that you want to save these scripts that you're working on. So on my desktop, I have a folder called PiLAF R, and that is where I have saved this, and I'm still going to save it as well. So usually, I think you can also go through session and set working directory and choose directory. All right. But if you've not, if you are confident with this, you can always do this. Write the code, then pick the address of that folder and paste it here. All right. Then when you paste it, don't forget to change your, if you're using Windows, you would have a backward slash. Where is backward slash here? Okay, yeah, you have a backward slash. But if you are using, you have something like this. So you have to change it to forward slash, or else you have errors. So that's why I just prefer coming through session and set working directory, choose working directory. You can always click wherever you want to save your work. All right. Control Enter. We'll run this line, set working directory. So presently it's setting my working directory to PiLAF R on my desktop. All right. Okay. Now, if you have your R scripts on, and while I've been talking on the PowerPoint, it must have told you to install some of these packages that we have here. If you are online, of course you are. Now, I intentionally put this here, R tools. It's good to have R tools installed on your system while using R, because some packages would not work if you don't use R tools. Usually R tools is used to build R packages, and while some of these libraries work with R tools, so to prevent a lot of stress to download it, and that is why I put this link here for you to download and install, maybe after the class. All right. Now let me just look. Okay, yeah. So I'm going to run these libraries now. If you don't have the ISLR and caret, I'm sure if you've been in this class for like 2 times, you must have installed tdvers. So we are not strange to tdvers again. Like I said, tdvers is a library, or is a container of different libraries, the ggplot, the dplyr, and a lot of them. Now, the ISLR has the data we are using, the loan data I told you about earlier. It has the data we are using, and we'll be bringing out the data from there. While caret is a machine learning library, very, very good. Like, it is very, very vast. If you are doing anything that has to do with machine learning, just install caret and tdvers. You should be good to go, except for 1 or 2 improvements you might want to add to them. So caret is a very important library you should have, and you should load most times when you are doing your work. Then you can also download and get familiar with documentation on caret. Like I think I said it earlier in the first class, that all of the libraries come with their own documentations, the official documentations you can get familiar with. And I showed how you can get them even in your R. All right, I'm just trying to say those things while my caret is loading. It's quite heavy, so it's taking a few minutes. All right, so we'll be using these data sets called defaults from ISLR. Now, because this default data set is the only thing we are bringing from ISLR, you might not want to install this library. So when you don't install the library and you want to use something out of that library, you don't want to install the library, maybe because your system has a low memory, or you just don't want to use a lot of computer power. You can call the function out from the package like this. All right. Now, another reason why we use functions like this from a library is, look at my tdvers here installing. It says that there's a complete with dplyr, there's a complete with start or filter and lag and all of that. Now, if it's saying that it has removed start, this function starts, and it has used dplyr instead, it has replaced with this dplyr. But if there's a function in start that I want to use, if I want to use this filter, I'll have to use it this way: start filter. If I have to use this filter from start, I'll have to use it this way, because loading tdvers has removed start, and it has replaced it with dplyr. All right. Although filter is also there, I'm just saying this because based on my experience, sometimes when libraries are conflicting and you need to use something from the one that has been overridden, you might need to get familiar with how to use functions straight from libraries. All right. It's still installing my caret and loading my caret. All right. So while we are doing that, let's just get familiar with data. Now, this data set contains the following information about 10,000 individuals. So that's a large data set. Now, the first column is defaults, which is our independent variable. Now, we have it indicates whether or not. Yes, that's what I'm saying. That we are not using an external data. We are using the data that comes with ISLR, and the data is called defaults. Yeah. So in case your system has finished loading your carrots, you can just run this, run the line 20 and 21. Over there, it might be 21 and 22 because I just removed one line here.
Thank you, sir.
All right. So we are using the data from ISLR package. So we are passing this data inside the ISLR package. The data is called defaults. So we are passing it into an object called data. Then we are running summary data. All right. So after like, I'm just trying to wait for my carrots to finish loading. So that's why I'm explaining the data sets in advance. All right. So the first column there is defaults, and it indicates whether or not an individual defaults or not. And it says yes if the person has defaulted, and no if the person has not. All right. Okay. So my carrot has finished installing. So I'm going to load both of them together. All right. Then the second column is students. Indicates whether or not an individual is a student or not. Again, this is a yes or no. So you can see the defaults. We have no, 966, 9,666 that are not defaulters, while 333 are defaulters. The second column. So default is a categorical variable because it has two levels or two factors, no and yes. While student is also a categorical variable, no and yes. You are either a student or not. If you are retired, you are not a student. If you are working class, you are not a student. All right. So we have 2,944 students, while those who are not students are 7,056. Then the third column is balance. Balance their bank accounts, of course. So average balance carried by an individual. And the last column is income. So I can show you the data by clicking data here. You can see we have 10,000 observations of 4 variables. All right, so these are continuous variables because they have minimum, first quarter, median, their mean, and all of that. All right. Okay. So you can see the data. We have defaults, we have students, we have balance, and we have income. So the objective here is that we want to use students, balance, and income to predict defaults, whether a person will default or not. Let's assume we are an existing bank that has history of 10,000 people who have borrowed money from us. Some of them have defaulted, some of them have they were compliant in returning the monies they owed. Now we have this data. When a customer comes, we want to collect, we are interested in 3 information about the customer. Is the person a student? What is the person's balance? And what is the person's income? If we know these 3, we will be able to predict whether the person will default or the person is a type that would comply with their payment methods. All right. Okay. So before we get into logistic regression, now what I just said earlier, what I just said now is a classification problem. We are classifying people whether they are defaulters or not. So now we are starting from contingency tables. To create tables, we've seen that we have 2 factor variables or categorical variables in this data set. Now we want to present them in tables. Now to show the frequency table of the categorical data in R, this is what we do. We use the table function. Table, then data. Data is the name of the data sets, the assessor and defaults. All right. So I can say assessor without saying what it means because we've come a long way here. So here we have no and yes. Of course, this is what we've seen, what the data summary has given us. All right. We have no and yes. All right. So yes is 333, and here also we can see 333. The same thing. If we want the proportion to be reported instead of the exact frequency, we can do prop.table. So here the proportion is, of course, we can interpret proportion in percentage. So 96.67% of them were compliant. They complied among all of our customers. 96.7 of them complied, while about 3.3% of them defaulted. All right. Now we can create contingency table as well. Now, if you want this to be actual percentage, you can just add times 100 here after the code, times 100. The difference between the normal frequency table and the proportion is the prop.table. So if I run this times 100, it's going to multiply the values in my table. by 100. So you can see what I was saying here, 96.67, 3.33. All right. So for contingency table, like I said, we are contingency table is a table that has row headers and column headers. So they intersect and shows us some marginal or some joint values. All right. So now we are doing table not just for defaults, but for students. Remember in the PowerPoint, I said whatever you want to come in as your column. Okay, yeah, as a column header. The column header is the one that's is in the y-axis, while the row header is the one that comes up the row heading. All right, so the column header comes first before the row header. So okay, so here I'm assigning two categorical variables and passing it into the table, and we are giving it an object name, table underscore table. Now, if I call table underscore table, I have my contingency table. I have the no yes, no yes. Okay, we have the no yes and no yes. All right, so now something just occurred to me now. After this class, you might try to also run the logistic regression for the no's as well, because what I'm trying to do here is to run it for the yes. Now, like I said, whatever we are interested in should come first. So we're interested in those who defaulted, and then for the treatments, those who are students. So how do we bring this yes to the first position, and how do we bring the yes here to first position? Also, how do we change this no yes, no yes? Because if I have not explained which one comes first and which one comes second, you might not be able to know if the row header is talking about the students, or the column header is talking about defaults. All right. Of course, if you add them together, the one that gives you 333 should be students. All right. Now, make yes come first for both. So now, this is what we are doing. We are bringing the column defaults out from the data sets, and the relevel. There are two ways to do it. So I'm using the first one for defaults and the second method for students. All right. So the relevel function would tell R to make yes as the first option. I'm going to run this as well for students. Then let's see table again. Table. I'm writing this inside the console. Table underscore table, and here we have. Let's wait for it. Okay.
So we can't hear you again.
Yeah, I was waiting for it. Yeah, I'm still here. Okay. Now, we still have the no yes and no yes. I just want to make sure that this is okay. All right. So now we have the yes come first for the row headers, and the yes come up first here as well. All right. So you can see 2817 here and 127. Then we have the 127 here and 2817 here as well. All right. Now, another thing we want to do, or we're interested to do, is to put actual to change the names from yes no to something more descriptive. So for the table headers, we are changing students, and we are changing yes and no to students and non-students. I said earlier that those who are yes for the students column are students, while those who are no are non-students. Now, okay, so this is my own definition for them. So I'm calling the yes students and the no non-students. Then again, I'm calling for the default column as well. I'm calling those who were yes for the default column, I'm calling them defaulter, and those who were no, or who are no, as compliance. So I'm going to run everything together and call the table underscore table once again. And let's see what we have. So we have defaulter, compliance, students, and non-students. Yeah. So among the students, we have 127 defaulters. We have 2,817 who were compliant. All right. So it's much, we can understand it better now. Although for R has understood it like the way it was, but for us, it's important for us, for the sake of interpretation, we need to do this as well. So, but if your categorical variables are explicitly explained, you might not need to do all of this claiming. All right, now graphical representation. How can we look at this? For it's good to always show things, not just give values. All right, so we have colors, two colors, because of course we have two variables. Now, bar plots, table underscore table, and color equals colors. Now this is not ggplot, it is just R base, it is R base function. So you won't see ggplot here. Just to show the appropriate charts for contingency tables or even for tables. All right. So if, you can as well put, if you have a name for the table, you can as well put this here. All right. So we have the defaulter and the compliance. Then we can see the legend as well. Another way we can use to represent this contingency table is the group bar charts. The group bar charts. So the difference between this stack bar charts and group bar charts is that it's just this argument beside equals true. Where is it here? Okay, yeah, I've seen it. Beside equals true. That's the only difference. So if we run this, it would bring down the other factor beside it. So we have the grouped bar charts here. The other way of representing this is the mosaic plots. The mosaic plot is also simple, very straightforward command, and it just shows like an area plot and gives the appropriate proportion for all the categories. All right. Now, back to our contingency table. We've had the simple contingency tables before. We can check their row sums and the column sums. Whereas the sums by row. All right. So for the contingency table, the sums by row is for total students 2944, non-students, blah blah blah. Then for column as well, the defaulters we have 333, and the compliance we have 9,667. You can see still agreeing with what we have from the tables, from this basic table as well. Now we can add this to the contingency table. We can have the margins, the sums by the column and the sums by the rows. And the argument to do that is add margins. Add margins will give us the table and the row sums and the column sums. Ordinary add margins, then the table. Table is what we have assigned the contingency table to. So anywhere we use table, it knows we are talking about the contingency table. All right. So this is the row sum, and this is the column sum. That means it's adding the columns. 127 plus 206. We have 333. 2,817 plus 6,850. We have 9,667. Now, what if you're interested in just this row sum and you're not interested in column sum? All right. So what we do here is to put margin equals 2. Margin equals 2, we add row sum, while margin equals 1 argument, we'll add the column sum. All right. So, okay, this should be column. All right. So let's see what I'm saying. So we add margins, ordinary add margins, we add for both row and column, while adding the margin equals 2 limits it to only row sums, while margin equals 1 limits it to column sums. And see, this has the column sum and the other one has the row sum. Now we can also make it much more interesting by adding mean to our margin. I mean, reporting mean instead of sum. There are also ways you can report mean and sum and so on. But because the contingency table is just an introduction to where we are going tonight, we'll just be looking at mean. All right, so we have the mean per row and the mean per column. Of course, the mean is 127 plus 2817 divided by 2. 206 plus 6850 divided by 2. All right, so it gives the mean and the mean here as well, which can be reported. All right, so also for the 2 by 2 table, we can have the proportions. Then if you multiply it by 100, it gives you the exact percentage. Proportion is between 0 and 1. Between 0 and 1. While if you make it percentage, it gives you the exact percentage. All right, so if you add all of this together to give you 0. Now, okay, so we've done this as well before, calculating proportion by row and all of that. Now, another thing, like I said, we can do with chi-square. But before I go into chi-square, let me just pause for 1 minute and ask for questions on the 2x2 table, the contingency table rather. So I can call it contingency table. Next week, it can be called confusion matrix, or what other name. It has quite a few names. All right. So for chi-square is a test of association between two categorical variables, just like when we did correlation. Correlation is between two variables, two continuous variables. All right. So the chi-square, we've also done chi-square before. In fact, I remember one of our prof's class, I think before the ANOVA, we did chi-square, we did Fisher's test, I think there was another G test, and so on. But let's quickly revise chi-square and see what we have. So checks if row and column variables are related. We are still talking about from the contingency table. To check if the rows and columns are related, we use chi-square. The chi-square measure goes from 0 in a case where there is no independence between them to n q minus 1, and this formula. Q being the minimum between number of rows and column. All right. Now, the bigger the value, what we are saying there is that the bigger the value of chi-square coefficients, the stronger the association between the row and column variables, categorical variables. So the bigger the value of the chi-square estimates, the more the association, and we can also say the more it is significant. All right. The null hypothesis of the chi-square test is that no relationship exists between the categorical variables in the population. That means they are independent. All right. Now, for the 2x2 table that we just did, remember what we assigned into table is students and defaults from the data. All right. So to run chi-square, we don't need anything much. This chi-square, the CHISQ dot test, is a formula, or is an argument, is a formula from RBase. It's a function from RBase. Function is what I want to remember. So running this will give us the chi-square estimate. This is the x squared, that's the chi-square, 12.117, and the degree of freedom is 1, because n minus 1. Our n is 2. So p-value is 0.0, like 20.4997, which is less than 0.5. So we can conclude that the variables are independent of each other. So because this is less than 0.05, we reject null hypothesis. Remember, null hypothesis says that the test is that no relationship exists between the variables. So if you are rejecting the null hypothesis, we are saying that there's a relationship between them, between the two. All right. Now, that is on chi-square. Chi-square is where we'll be stopping here. We are not interested in the Fisher's test here. It measures the same thing, but if you remember in that class, which you can go back to revise, there was an assumption that we checked that we said that we can use Fisher's test when one of them is less than 5. When I think when the observation is less than 5 or so, we use the Fisher's test. But however, it's still measuring the same thing, association between two categorical variables, which you can use chi-square for. All right, for odds ratio, we are getting into today's work more. An odds ratio greater than 1 indicates that the condition or events, this time our condition or the event that we're interested in is yes for default. That means the person is a defaulter. So an odds ratio greater than 1 indicates that the condition or event that a person defaults is more likely to occur in the first group. That's the reference group. So when we're talking about first group here or reference group here, we're talking about students. And in the student data, we said we have the students and non-students, and we have made students to come first, then the non-students to come second. So the first is always the reference point. So when we have an odds ratio greater than 1, we are saying that the event of being a defaulting customer is more from the student group than the non-student group. All right. So why I took my time to write all of this here is that I know how tricky odds ratio can be when you are trying to interpret it. Sometimes we put it upside down. And an odds ratio less than 1 indicates that the condition of events is less likely to occur in the first group than the second. All right. So when it's greater than 1, the event is more likely to occur in the first group. When it is less than 1, the event is less likely to occur in the first group. So we are mentioning first group because it has been made, the first is always used to as reference, rather, as reference. In other softwares like SPSS, you can choose whether you want to use the first or the second. But for here, you have to make it the first. It's very, very important for proper interpretation of your model. All right. By default, R is going to use is going to arrange it alphabetically, and it's going to use the first one. One of the ways to measure the strength of association between two categorical variables is an odds ratio. All right. So here I'm talking about the Fisher tests. The Fisher test, why we did chi-square? Chi-square test will not give us odds ratio, but the Fisher test can give us, or will give us odds ratio. If you run, if you run this, you can try later by just putting the data assessor, that's the $sign defaults, data $sign students. You would have all the outputs there. All right. So, however, to get a proper or a more robust output for odds ratio, we'll be using this library called epi tools. I guess the full meaning is epidemiological tools. They are the ones that use a lot of odds ratio. All right. So you install epi tools and then load library epi tools. All right. I'm going to load mine now. So in the epi tools, there's a function called odds ratio. So you just insert your contingency table into the odds ratio. So by default, what it does is it uses the method called WALD. All right. So just put your contingency table, and you have a long range of outputs. All right. So let's see what we have here. So you can see we have the contingency table with both margins there. So we have students and defaulter, students compliant, non-students defaulter, non-students compliant customers. Now the odds ratio comes here. Now, so because student is the reference point now, so we are saying that that's why the odds ratio is by the non-students. Here the odds ratio is greater than 1, is 1.44. If you go back to what we just read up a few lines up, we said when the odds ratio is greater than 1, we are saying that it is more likely that this event of being a defaulter, it is more likely to occur in students than non-students. All right. So that was what we said up there. All right. So here where the odds ratio is greater than 1, we have 49.9 after 1, or can even say 50, 1.5. So that means students are more likely to default than non-students. That's for this. Then we also have the lower and the upper, that's the interval, and 95% confidence interval. All right. Now, the significant value for this odds ratio. So this odds ratio is significant. It is less than 0.05. So what does that mean? It means that we are confident that 95% of the time we will still get something in this range. Now, when we perform these experiments again and again, the odds ratio for students and non-students defaulters will be between 1.19 and 1.87. All right. So this is our point estimate for the odds ratio, and this is the interval estimate for the odds ratio as well. All right. So I said to get clean outputs only for the odds ratio. So sometimes, a lot of people would not like a lot of values coming out this way. So if you want only the odds ratio without the table, of course, we've done the table before, and without the p-values, you can run this as the odds ratio function. The table by table, that's the name of the contingency table. Then the method is WALD, and then measure. Then it's giving only the measures. Then it gives the odds ratio estimates the lower and the upper confidence intervals. Okay. All right. So I said we reduce this to mean that the student defaulting. Okay. So what happened here was that I think I did not rearrange. So the odds ratio it gave me here was 0.7. 0.7. I already did some things before writing this. So you can see this odds ratio is less than what I have here. It's less than the 1.4 that I have here. So all right. So this wouldn't be the case. This won't be the case for this present odds ratio. All right. So very soon I'm going to show you what happened, why we have 0.7 here. Yeah. Oh, we have 0.7 here. All right. So here in this last line here, I said this is how we came about the odds ratio is that students defaulting, the probability of student defaulting divided by students compliance, then over non-students defaulting and non-students compliance. All right. So that's how the odds ratio was calculated. Okay, so before I move further to start logistic regression. And do we have any questions pertaining the odds ratio?
Hello, good evening, sir.
Good evening, sir.
My question is that what you obtain, is it odd ratio or log odd ratio? Because
It's odds ratio.
Okay,
Yeah.
so the odd ratio is achieved directly without
We've not started the logistic regression. What we are doing, what we've done so far is the contingency table and getting the odds ratio from contingency table.
Okay.
So now we are going into logistic regression. That's where we do the log, where we see the log odds ratio. Do you understand me?
So when I keep quiet, you see this is why I keep quiet.
When you come back,
Hmm?
when you come back,
He said,
No, whenever
you go outside.
okay, Mr. Victor, are you with us? All right. If there are no more questions, let's continue with logistic regression. All right. So far what we've been doing is, before we go into any tests, we prepare our data, we check assumptions. Sometimes after developing the model, we check again for assumptions to know how well we can trust those models. All right, for logistic regression, you have to make sure that all your categorical data are factor. They have the factor class. All right. And how to check that? Remember, we have two categorical data here, the defaults and students. We have the defaults and students. All right. So if you check the class for defaults, it says it's a factor. And if you check the class for students, it's a factor. All right. So this is a sort of a perfect data set. And in this regard, anyway. So the question is, what if it is not, it didn't come as factor? Okay, so we'll be using a function called as.factor. That was why I was smiling there, as factor, to change whatever categorical data that we have from whatever class it was before to factors. I have done that before, so I can't remember which class, but I know I have done that before. So you can check previous videos for that. Now, to improve the accuracy of logistic regression model, it's important to do three things. I think three here. Remove potential outliers. Make sure that the predictor variables are normally distributed, and remove highly correlated predictors to minimize overfitting. The first one, remove potential outliers. The second one, make sure that the predictor variables, the independent variables, are normally distributed in case you have continuous variables there. Then remove highly correlated predictors to minimize overfitting. The presence of highly correlated predictors might lead to unstable model solution. All right. So in the regression class, the first regression class that I took, we talked extensively on multicollinearity and this overfitting thing. So we can check that. But I would like to stress these outliers, because outliers can just like their name, they can be outliers. They can distort results. One outlier or two, depending on how large data set is, or more rather, can distort the results. Now, if you remember from all of the things we've been saying from the beginning of this class, the box plot is a very wonderful way of visualizing your continuous variables. So here we are plotting box plots for balance. So I wrote here that outliers exist for balance. Okay, so you can see we have so many outliers. This is the 25 percentile. This is the median. This middle line here is the median, and this is 75 percentile. Now, to remove these outliers, we want to remove these outliers. Now, this cap here, the upper cap here, is this point is called this upper part here is the quarter, the 25% quartile. No, the 75 rather, plus 1.5 interquartile range. Now let me explain. So for the quartiles, remember I said this is 25% and this is 50th, that's the median, and then the 75%. Now we want to get these points from here. Already when we ran summary gave us anyway the summary. When we did the summary for the whole data sets, it gave us these values. But let's see how we can call it out ourselves. then we use it to filter out those ones that are higher than these points here. We filter them out. Now, quartiles, the quantile data balance. So from that variable balance, now give us the 25 percentile and the 75 percentile, all right, as a vector. Now, if there is any missing value, remove it. All right. Now, for the interquartile range, IQR is the function in R that gives you the interquartile range. The interquartile range is the 75 percentile minus 25 percentile. All right. So the formula for these lower points, this lower cap here, remember outliers can either be above the lower cap or below, above the upper cap or below the lower cap. All right. But in this data sets, all the outliers are above. All right. But I just did this here just in case you need it for something else. Oh, sorry, I have not run this. All right. Now in SS, what I've done so far is I want to know these points. I'm not interested in these points because there are no lower outlier. So I want to know these points. So that is the upper. Now, if I call upper now, yeah, so you can see we have 2193175. All right. So now what I want to do is that I'm subsetting this data because the name of data is data, if you've not forgotten. And using the balance column, I'm saying that subset every value that is below upper here. Every value that is below this value. All right. So this is what this line of code is saying. So anything that is above this value will be removed. And yeah, their rows will be removed using the balance column. Now, we have 9,969 observations. If you remember before, at the beginning, we had 10,000 observations. Now we have 9,969 observations. 31 rows have been removed. That means all these things we have here, they are up to 31. All these points, data points that we have here are up to 31. All right, so what we can do is I'm going to run this box plot again and see what's, yeah, see what we have. I'm waiting for the new box plots. I want to confirm if the outliers has been removed. All right. So now we have this. We have one that is just by this point, which is fine because we have 9,969 observations. So it's fine. We can forgive this guy. All right. Now we should check the other variable as well. Box plots. What's that other one? Income. All right. Okay, so income is fine, no outlier. All right, so we have taken care of the outliers, and now we can go ahead to develop our model. All right, now, why I'm doing this here, as I split data into two using the 80-20 rule. Why I'm doing this is because I'm going to develop the model using the 80% of the data. The data is much. We have close to 10,000 data sets. So dividing it into two, I'm going to have one part as 80%, the other part as 20%. So what I want to do is that I want to develop the data using the 80% part, then use this to test it and see if it's going to if it's going to predict this 20% properly. Then I can be sure of the accuracy of my model. All right. To do that, we've used set.seed before, and we know that the value in set.seed can be anything. It can be 1, it can be 2023, it can be 12, it can be anything. So the essence of the number is that if I use 1 and you all use 1 as well, it will have the same value. But if I use 1 and someone else uses 5, or any other thing, we will not have the same thing. So it gives R like a procedure to cut my data, because it will choose it's going to choose 80% randomly and choose the 20% randomly. It's not like it's going to cut the first 80% away and the 20%, the remaining 20%. No, it's going to be random. All right. So here we are specifying that the way it should cut is 80 and 20%. Of course, we know that 80 and 20 is 0.8 and 0.2. You can decide to use 0.7 and 0.3. Mostly people use between 0.7 and 0.85. That's what is very common, depending on how much your data sets are. Anyway, all right. So for the 80%, we'll call it train, and for the 20%, we call it test. All right. So if you run this, of course, the 80%, I mean, the test is, there's this question mark. Is this question mark? No, exclamation mark rather. Exclamation mark means not among the sample. Remember, this is sample, and we have true, false. So putting all the sample here puts all the true there. I remember in the slicing procedure, we said 0.8 first, then 0.2. If we put 0.2 first, 0.2 will go for the train, while 0.8 will come for the test set. All right. So what I'm just doing here is just to partition the data into two. The first one, 80%. The second one, 20%. All right. So you can see here we have the two data sets here. We have train and we have tests. The train is 7,908 and the test is 2,061. They both have 4 variables. They are from our main data set data. All right. So let's keep that somewhere. Let's fit the first logistic model. I mean, whether it's first or not, but the first logistic model we are fitting is a simple one. Yeah, it's a simple one. And what we want to do is use income to check the association between income and default. So the income of a person, how does it associate or relate with whether the person would default or not? Remember, income is a continuous variable. All right, so we won't have any more sophistication here. So, like I said earlier, GLM is the function. LM is for linear model. Why GLM? Generalized linear model. All right, and the family is binomial, 2 outcome. All right, so data equals train. Okay. Or we can use data equals data anyway. Yeah, because we're not. But let's just go on. So the name of model is model simple. So then the summary is going to give the output of the model. Let's see what we have here. So in case for those who have not been in any of the regression class, default and this sign is called tilde. The default, that's the variable we are predicting. The dependent variable comes first. It comes first. Then the independent variable or variables come after the tilde sign. So by the left side of the tilde is the dependent variable. By the right side of the tilde are the independent variables or variable. So for this one, because we're looking at simple logistic regression, income first on defaults. So by the time we get to multiple, we can now check the others on defaults. All right. So now the output here is going to give us in scientific notation. You know, when you have a lot of zeros before your value, it transforms it into scientific notation. However, I have put this function here. Control C. If you run this and the summary together, it takes care. It tells R not to present it in the scientific format and present it normally. All right. So let's see what we have here. All right, yeah. So you can see the p-value. So the p-value here is 0. Normally it should have written 0.2 e raised to power or something. But here it has written it out in a plain figure. All right, so for the intercept, we have this. For the income, we have very small association or very small association with defaults. Now let's see, what does this mean? We have 3961. Okay. All right. So for me to have, or for us to have outputs that corresponds with the interpretation we have here, because I don't want to be saying apology here and again, I'm going to change the data here from train to the complete data. All right. So I'm going to run everything all over again. All right. Okay. So while it is running, what I did was to fit the logistic regression model, which I showed in the PowerPoint, using the outcome. So the constant is what we have here, 3.48, blah, 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 which is what the person that asked the question about log is saying. So it gives us the odds ratio in the log form. So 3 points, blah, 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 and that's why you're using exponential in the model, like fitting it in the model gives us back the probabilities. All right. So the logistic equation can be written as, the model is still coming up. I'm just using this to explain. So this is the constant, and then this is the coefficient for income. And again, 1 plus exponential of the constant plus the coefficient times income. So that's fitting the model we have for simple linear regression. For simple logistic regression that I showed earlier in the PowerPoint. I'm trying to show it again. Oops. Okay, so this is what I was doing in the R scripts. Of course, R scripts I can't write this way on the R scripts. So this is exponential, and the model constant is the B naught. Then income is X, and the coefficient for X is the B1. So fitting all of this will give us the probability of income and the chance of default given that income. All right, so we have our outputs now. So let's see. Okay, so we have 3.258. A little difference. Yeah, we have a little difference here. Okay. All right. So, however, to fit that, we just have to put 3.258 Control C and put it here. Probably I used a difference. Okay, it doesn't matter anyway. And then here, and put it here. Okay, then copy all of this, Control C, and put it here. Okay. All right. So what does this mean? It means that for single, a unit increase in income would increase the chance of someone's defaulting by 0.00, like very very small amounts. All right, by that value, like 0.000573. All right. So interpreting the model, we have the null, and let me show you. Okay, so we have the null deviance and the residual deviance. As a rule of thumb, the smaller the null and residual deviance are, the better the model. So the null and residual deviance, so I'm going to spend time here so that, because the same explanation for multiple regression as well. Multiple logistic regression as well. All right. So null and residual deviance. Null deviance suggests the response by the model. If we only consider the intercepts, the lower the value, the better is the model. Now, the residual deviance indicates the response by the model when the variables are included in the model. So again, the lower the value, the better the model. All right. For the intercepts, that's a beta null indicates the log of odds of the whole population, of interest, to be on predicted reference class with no predictor variable. So if you are not considering income, if you are not considering anything, the equation constant is giving us the log of the odds. So that was the question that was asked earlier, that he thought that logistic regression gives the log of the odds. Yes, it does. But as at then, we were doing odds ratio based on contingency, the contingency table. All right. We can convert the log of odds back to simple probabilities by fitting it into the model using the sigmoid function. And that is what we have here. So if we run this, is it the same thing? Is it the same thing here? This is 3.4. All right, so let me put the constant here. Although it's still going to be high. When I calculated it earlier, it was high. So let's see. And I'm going to call P 5.96. So probability of defaulting without any predictor variable is very high. So what are we saying? That as the bank, if we don't, like, we are putting everybody, as long as we don't know their income, we don't know if they are students, and what's the other, we don't know their balance, we are putting everybody into the defaulter group. We are saying that everybody has the has a high potential of defaulting, of not returning our money, which is, I think, is a good assumption, which should make us want to investigate people more and more. All right. Then again, for the intercepts, you can, for the intercepts, that's the coefficient of income. We can also calculate the probabilities as well, given the income. All right. Now the intercepts, the intercepts of OR 30.3 indicates that the odds of an, okay, we can read this up. All right, so as not to waste time. Now, predicting from simple linear regression. Now, using this formula or model, for each that model we fitted, for each new income value, we can predict the probability of individuals to default. So we are creating another data set with 2 values only, and it's called new data. So this person, remember, we used income to predict, we want to use income to predict whether a person will default or not. So income is continuous variable, and we have income equals 2,000 and 1,800. Those are their incomes. If I call new data here, view new data, you will see it's a data set actually, but with 1 column, and the 1 column has just 2 observations here. All right, let's go back to the scripts. Now, probabilities model simple. That's the model that we created, that we developed using income and defaults, piped into predicts new data, that is the 2,000 and 1,800. So we are putting it into that model. We run this here, and here, okay, yeah. Let me see what we have. The probabilities we have. I'm just running only the probabilities. So for the first entry, that's what 2,000. The probability of this person defaulting is 96.33, blah blah. While the probability of the other person defaulting is also 96.33, almost the same thing. All right. Now, how does this? Because this becomes our response variable, the dependent variable. So how do we make it a yes or no? We have in the original data set, we have yes or no. How do we make it yes or no? So we classify it that any probabilities that is greater than 0.5, that person is more likely to default. Otherwise, the person is less likely to default. All right. So the predicted classes, we have if else probabilities. If the probability is greater than 0.5, yes. Else, no. That's what that line is talking about. So if we call that, we have, so for the classes now we have yes, yes. So remember I said once the probability is greater than 0.5. So here it's greater than 0.5, it is yes. And here it's greater than 0.5 as well, it is yes. So the prediction for these 2 new customers is that they are likely to default. They are likely not to be able to return the money that they want to borrow, judging from their income and from the model we have created from about 10,000 customers we have had before. All right. So before I go into multiple logistic regression, our time is fast spent. So just one simple question, or maybe when we are done, I can try and rush this in 10 minutes. Then the remaining 5 minutes, we'll try to get feedback or question. All right. So for the multiple logistic regression model, we have more than 1 independent variables. So this time around, we are using all the 3 independent variables: the students, the balance, and the income. So a way of doing this is to put it this way. And another way of doing it, I can do X and put points here. So the point means that in case you are going through other materials and you see them do it this way, this point means use every other column. All right. But in the case where maybe you have like 10 columns and you're interested in using 3 columns out of the 10, you can specify them out like this. So that's the only difference between the simple and the multiple. So for the simple, we had only income in the right hand side of the tilde, while for the multiple, we have all the other independent variable. All right, so let's run this and check the coefficients of the model. All right, so don't forget again that you can use summary to check every other thing that the model has. So without wasting further time, we do that. So the sciped function again would prevent it from bringing out the model in scientific formats to spell all the values out. All right. The other simple logistic regression, I forgot to check whether the p-value is significant or not. All right, so for this, but it's only balance that is significant. All right, so we have, this is the p-value, and the constant is, I mean, the intercepts here, the constant is significant. We are not interested in that. But here, among all the independent variables, the balance is significant. Yeah, and it's very, very significant. So if we are looking at which one is followed, because there is something we're going to do now, it's called variable importance. It judges how important the variable is using their p-values. So the lower the p-value, the more important your variables are. All right, so balance is important while others, I mean, is significant while others are not. All right, so let's see how is this interpreted. Now we can get their odds ratio, because this, like we have said earlier, is the log of the odds ratio. That's the estimate here. So we can get their odds ratio by running the exponential, the exponent of the coefficients for all the coefficients in the model. And this will do that for us. That's the exponent, C bind, that means OR, that's operation, sorry, not operations, odds ratio is equal to the coefficient of the model. All right, the coefficient of the model. Then also the confidence interval of the model. So what this is going to give to us is like a small table that has the OR and it has the intervals, the intervals, yeah, the confidence intervals for the OR. All right, for the operation, why do I keep calling odds ratio operation? Sorry. So for the OR, the odds ratio, we have students no. Now this is very, very important. Remember, for the students, we have yes or no. We have categorical variables. Now, in some cases where we have 3 categories, 4 categories, dummy variables, you can create your dummy variables personally, or I'll create dummy variables for you in the estimates. Now, what does dummy variable does? What it does is, it makes the first, I've been emphasizing on this, it makes the first, in R is alphabetical, it makes the first factor as reference. So because we have made, normally no comes before yes, n comes before y, which is what we've seen from the first part of creating the table, the simple table, the frequency table. Now we have now changed it to make yes come before the no. So that's why yes has become our reference. That's yes for the person who is a student. So now we'll be interpreting this in reference to students. Now, so for this, we have students are less likely to default than non-students. If you remember our interpretation for odds ratio. So because this odds ratio is less than 1, we are saying students, that's the first group, a reference group, are less likely to default than non-students. All right. Now, then for balance and income, they are not categorical variables, so there are no dummy variables for them. So we say the odds ratio is 0.99, and it's interpreted as for a unit increase in balance, the odds of defaulting decrease by 0.006. And that's less than 6%. That's like 0.6%. Let me see. Okay, yeah, it's 0.06, because that's 1 minus this. Yeah, 1 minus 0.994. So that's 0.06. Yeah. Okay, sorry. Let me just do the math. 1 minus 0.9943. Okay, and so that's 100. That, yeah, okay, I'm correct. I was correct initially. It's 0.6, not 0.0. All right. So the odds of defaulting decreases by 0.6. All right. So then for the other guy, income, for a unit increase in income, the odds of defaulting decreases by 0.1%. I think, and it's a good thing, of course. So because if the odds are defaulting, that means they are more likely to pay up by 0.1. It's just that that's the rate at which the odds is decreasing is very, very little. Well, yeah, it's very, very little. Having 0.1%, not 0.1, it's 0.1%. So it's, that means 10 of that would give just 1%, to get 1%. All right, so that's how this can be interpreted. Now, for the variable importance I just said, this var importance is a function from carat. If you run it, it's going to list the variables as their rate of importance. So it gives them a value. The highest value is the most important. So like we've seen, balance is very important, followed by students, whether a person is a student or not. Then the least importance is income. So whenever, for us as a bank, when someone comes, the first thing we look at is the person's balance. Maybe perhaps balance talks about shows how the person has been saving up. how disciplined the person is. I'm not sure. I'm trying to explain the data. All right. Now, multicollinearity assumption. We talked about assumption that the independent variables should not be correlated, should not be related. All right. So this is brought from the car package or library. The VIF is brought from the car package. If you don't have it, you can install it. Now, but if you have it, you don't have, because we are just using this function from it. So we don't have to call it and wasting time on it. So now for VIF, VIF value greater than 5 indicates severe multicollinearity. So we are safe if we do not have up to 5 value for VIF for each of the variables. So this is fine. Sorry, this is fine because students is 2.8, balance is 1.0, and income is 2.7 as well. Now, to use this multiple model for prediction, remember when we used okay, that's wanted to bring that. Yeah, when we were doing the simple logistic regression, we used 2 values as income, like one variable, income, 2 entries. But here we have used 3 variables to predict one thing. So to build the model for default or not. Now to predict as well, we have to use the same number of variables to do the prediction. So we are creating our new data. We are calling it new. So data frame balance, that is going to be the colon code balance 1,400. Income, another colon code income 2,000. Then students. So the students are going to be two entries, 1 yes and 2 no. In essence, we are looking at 2 students. They both have their balance to be 1,400. Their income is 2,000, and one of them is not student. One of them is a student. The other one is not a student. Yeah, 2 people working to the bank. They both have the same balance. They both have the same income, but the only difference is that one is a student. The other one is not a student. So let's view the data and see what it looks like. It is a data with 3 columns and 2 entries. So you can see the first person earns 1,400, income is 2,000, and is a student. The second person earns 1,400, income is 2,000, and is not a student. All right. So if you see, we don't know. The data available is not showing whether they are defaulters or not. We don't even have their credit score or whatever, their performance on other with other loans and with other banks. All right. So let's predict. Our model is MM. If you check for the multiple logistic regression, MM, like M model, M for multiple, then the data is new. So just bring the model and data and type equals response to predict the response. Now, it's predicted 0.974, 0.957 again. So again, high chance of defaulting. Now, okay. So again, we want to check how to, remember we split data into 2, the train and the test. And we have used the train to build the model. Here we are passing the tests. So the test is a new data set. We are passing the test into the model again and calling. Okay. Yeah. Now, if we have test defaults for the test, the default part of the test, we have if else, test default if it is yes, 1, and if it is not yes, it should be 0. Why we are doing this is because we want to check it with what has been predicted. If the default is the same thing as what has been predicted. So instead of the yes, no in the test default, where is test? I'm sorry. Okay, so instead of yes, no in the test, we want it to change to, if it is yes, it should change to 1, and if it is no, it should change to 0 for the default. Okay, so you can see we have no, and we have yes at some points. So this code here is changing it to 1 and 0 because the predicted value is not going to come as 1 and 0. It comes as numbers. So again here, okay, so I've not run this. Let me run. Now, for the predicted value that we've calculated, we are saying any value from the predicted that is greater than 0.5, you should make it 1, while otherwise it should be 0. Okay. All right. Now, this here, the mean value for predicted class, that is the same thing that matches as the test defaults, because we now have 1, 0, 1, 0. Once they match, it should make them, this is a Boolean expression. So if it is true that they match, it makes it 1 or true. If they do not match, it returns false. So like I said, that in a previous class, that every true in every Boolean output that is true, even if it's a data set that is true, R sees it as 1, and false, it sees it as 0. All right. So for every true, every time the predicted is the same thing as true, I mean, as the default, then it returns true. And remember, true is 1. So to get the mean, it gives us the average of, mean is average, like on the average, how many of them are true compared to the total. So for this mean, for this, it's telling us that 3.3% of all the predicted matches with the defaults. That's with the defaults from the tests. So meaning that the model is able to predict correctly 3.34 or 3.35% of the data. All right. So it's not too good, but it can be improved on either by bringing in more variables or by collecting more data to fit the model. All right. So from next class, we would see confusion matrix and how models can be evaluated more for their performance and all of that, sensitivity, specificity, and all. And there are several model estimations. But for this class, we are only concerned with model fitting and building the model. All right. So I have 2 minutes. 2 minutes more. I think someone is raising their hand. Do we have questions? Are there questions?
Yes, I have a question, sir.
All right, sir. Okay.
Thank you very much.
Thank
I have a question, and then I also have a request.
Okay.
To the question, you are saying that if the PiF is less than 5, it means that
Yes,
it means that there is
we do
no
not have
problem
multiple.
of multicollinearity. So suppose we check for the multicollinearity level, and one of the variable is more than 5. So how should we handle that?
So please, can you come back? Sorry, I was trying to read something.
I said, suppose if we check for the multicollinearity level, and one of the one of the independent variable has PiF that is more than 5.
Greater than 5. Okay.
How should we handle that before we
Okay.
continue to predict the model?
When we have a case of multicollinearity, then we can check for which, we have 3 variables here. We have 3 variables, and if balance, for example, has 7 point something, 7.7, 7.5 value for multicollinearity, you might try to check the chi-square or the correlation value to see which of the variables it is correlated with. Then what we do is remove one variable. So if it is correlated with, if balance and income are highly correlated, you can remove one, then fit your model. Then again, remove income first, then fit your model with balance and students. In a case where, then again, remove balance again, then fit it with income and students. Then you can check which of the models give you a better evaluation, a better accuracy score. Do you understand that?
Yes, I'm following. But my concern is that in the real life, like when people that are working in an organization come with their data, there are times that they will tell you that none of the variable is variable that can be removed. That all of the variable are very essential for what they are to check.
No, I think you should advise them. You can't say all variables are important. In fact, sometimes when you have a lot of variables, when you get to okay, so what we did today is like a little machine learning. We did test and train. Sometimes we do variable, it's called maybe variable engineering or variable selection, to perform some analysis, some simulations that will tell you which variables are most important in predicting an outcome. So I think they'll be doing themselves a lot of this harm by forcing you to use all of their variables, saying that you have to use all of them. When for each model, for each model or each method, there are assumptions that you should follow. If you don't follow such assumptions, you might not have a reliable model. That's the problem. If you run it with all of their variables, fine. But how reliable is your model, is what you have done. That's why those steps are needed. You go back and forth and change them and remove, then do some variable selection techniques and know which variables are actually appropriate for that model. So you can advise them on what you have seen. When they come and tell you all the variables are important, then you can run it and then call their attention to it and explain to them why some variables should be removed, why probably some transformations should be done, and so on. But saying that all variables has to be used to predict something, I disagree with that. Okay, hello, ma.
Yes, sir. I want to ask a question with respect to overfitting. I don't really know much about it, but I want to know if it has anything to do with a model not converging. Maybe you run a model and you're having a result that the model cannot converge or convergence is not achieved. Is it because the model is being overfitted or is not properly fitted?
Yeah, so
and if that arises, how do we I don't know.
Yeah, that would come up next week, because that's what we're talking about, the model evaluation. Today we've learned about how to make the model. So next week we're talking about how to evaluate the model, how to check the convergence and a lot of and overfitting, underfitting, and so on.
Is it also related?
So
sorry, sir. Is it also related with starting point issues or something like that? I don't really get that too.
I doubt it. Starting point is something from which model is that?
It's on structural equation modeling. I'm trying to fit a model. So
you are trying to link things.
I'm trying to
no.
But in this model, my model is unable to converge. And it's telling me when I try to look up what convergence means, it means I didn't fit the model very well due to maybe due to the input or the variables, the independent variables I'm using. So I don't know how
to. This is what I would advise. What I would advise is you check the assumption for the model you are trying to fit and make sure your assumptions are well met.
Okay, sir. Okay, sir. Okay. Thank you, sir.
Try and check that.
Okay. Yes, sir.